The next law we're going to look at is Charles's Law. Now, Charles's Law was declared in 1787, and he was describing the relationship between volume, but this time with temperature. So think about those four key properties of gases we're talking about. So there was volume, there was pressure, and there was number of moles. So if they are investigating the relationship between volume and temperature, then pressure and number of moles must stay the same. All right, let's show a little demo.
Hey folks, it's Dr. D here. In this demonstration, we're going to be looking at Charles's Law, one of the gas laws. Charles's Law relates the volume of a gas to its temperature. So the way that we're going to do this demonstration is we're going to use some liquid nitrogen. So I've got some liquid nitrogen right here in this container. This is called a dewar. It's like a really big fancy thermos. And I'm going to go ahead and I'm going to put on some special gloves to do this because liquid nitrogen is very cold. So it is minus 196 degrees on the Celsius scale or 77 degrees on the Kelvin scale. So that's 77 degrees above the absolute coldest temperature possible. So let me go ahead. I'm going to pour that liquid nitrogen here into this other dewar so that you can see what's going on. Now, one of the things that you might observe there in that dewar is it looks like it's boiling. And in fact, it is boiling because the temperature of that dewar is so much warmer, right? It was room temperature compared to the temperature of the liquid nitrogen that I'm pouring in there. Now, nitrogen, by the way, is about 80% of the atmosphere that we breathe, so it's most of the gas that is around you right now. All right, so I'm going to get this poured in there. We're going to allow it to stop boiling a little bit just so that it's easier for us to see. Okay, so now the next thing that we're going to do to demonstrate Charles's Law is we're going to put some balloons into this liquid nitrogen. So I've got a balloon here. And what we're going to do is we're going to put this balloon into the liquid nitrogen and see what happens. We like to call these a portable air container, right? Portable gas container. So let's go ahead. Now the temperature of this gas right now is the temperature in this room, which is about 24 degrees Celsius at this point. And what we're going to do is we're going to see what happens. So you'll see already that the volume of that balloon is decreasing dramatically. And in fact, it looks like it completely, all the gas completely is gone. It's what it looks like. In fact, it's not gone. It is just reduced in volume. So if I take this out and we look at what happens to it when we warm it back up, here I'll hold it so we can watch. We're going to see that as that gas warms back up, that in fact it was still in the balloon, and it's going to refill the balloon, so it's going to return to its original volume, the volume that corresponded to the temperature in this room. Okay, so there we go. So Charles's Law. Now, just to have a little bit of fun, I've got a few balloons. So we're going to see how many balloons we can stuff into this container of liquid nitrogen. So here we go. Now let's warm them up.
weirdly satisfying. So, what is the relationship? Well, what we watched was when the temperature decreases, the volume also decreases. When the temperature was then increased, the volume increases. This is when we had a consistent number of moles, so it was a sealed balloon, and then the pressure was allowed to be maintained through changing the volume, right? So you either have a fixed container where the volume can't change and then pressure changes, or you allow the shape of the container to change and then you can allow pressure to stay constant, but the volume will change. But how do we describe the relationship between volume and temperature? Well, instead of inversely proportional, we'll say that volume is directly proportional to temperature. In a mathematical relationship, we would just say volume is proportional to temperature, and it's a directly proportional relationship because the T's on top instead of on the bottom. If we throw in an equal sign, we have to throw in a constant of variation, so V equals KT, and we could say that K is equal to V over T. So that if we wanted to say we had V1 over T1, we could let those two K's equal to each other, and we'd say V1 over T1 equals V2 over T2. And this is the Charles law equation in the two-state form. Now, the most important thing about any calculation involving temperature is that for some reason, it matters. Well, actually not for some reason, I know why, but it matters that you do all your calculations in kelvins. And the reason why is that the conversion between kelvins and Celsius is an addition calculation. And so it's not, this is getting really mathy, but when we talk about proportionality, when we talk about volume and pressure, if you multiply or divide by something to change its conversion, you're doing that to both of them and it ends up equaling out. Whereas when you're adding and subtracting, you have to add and subtract before you do divisions. And so it actually alters the variable itself. So you don't have to know all that. All you have to know is that you must convert all your temperatures to kelvins for any gas law quick calculation. So that includes these ones as well as the ones that we're going to be doing in the next class. Now, luckily for us, the conversion is quite simple. If we're going from Celsius to kelvins, to find the temperature in kelvins, you take that temperature in Celsius and you add 273.15. Now, the hardest part about this, and the thing that I'm finding mistakes in answer keys, is that when you do addition subtraction, it's a different rule for sig figs. So when I'm introducing this new number into my calculator, I'm going to do 24.1 plus 273.15. I get 297.25. And then you have to be careful. It's not 3 sig figs. You have to maintain precision. So since this was to 1 decimal place, that's my least precise value, I'm going to answer this guy to 1 decimal place. So if this is a final answer, I would say 297.3 kelvins. So this thing that started as a 3 sig fig is now 4 sig figs, which generally is what will throw you off in future calculations, because you'll look back and you'll be like, oh, in the question I had 3 sig figs, but we actually used it as 4. So just be careful. And then if they wanted you to then convert your answer back to Celsius for the answer, you would do that the temperature in Celsius is equal to the temperature in kelvins minus the 273.15. So we would take that temperature in kelvins, that 200, and now that one's at precise to the ones. We would minus 273.15, and we would get, I feel like it's negative 73.15, but I'm having a doubt myself day. Yes, of course it is. You get negative 73.15, but precision, we're going to maintain it to the ones. So my answer would be negative 73. And again, kelvins are just kelvins, not degree Kelvin, just kelvins. Okay, so now that we're solid on that conversion, let's find the missing value. So I've set these ones up nicely for us where I'm giving you, so instead of putting it in a word problem, I've just given you the variables we have. We would set up that V1 over T1 is equal to V2 over T2. They've given us V1, T1, and V2, and they're asking us to solve for T2. Again, totally your call. If you're not comfortable with algebra, you can put your numbers in right now. You would get 2.3 divided by, now I have to change this to Kelvin, so 273.15. So 88.6 plus 273.15. gives me 361.75. And then I'm going to write that all down, but it's 4 sig figs in my calculation. So over 361.75, but that is 4 sig figs, equal to V2 is 0.5 over my T2. So if you're not comfortable with algebra, I mean, it's still not the easiest, but I would put my numbers in like this, and then I would rearrange and solve. The rearrange and solve part, let's do it with the literal formula. If you look at this one, it's the T2 that I'm trying to solve for. So the first thing that I would do is get the T2 out of the denominator. So I'm going to multiply both sides by T2. So I end up with T2 V1 over T1 is equal to V2. And again, when you get good at these, you'll stop showing the work. You'll just rearrange it in your head. But now we want to solve for the T2. So we're going to multiply by the T1. So we end up with T2 is equal to, we're going to multiply by the T1, and then we're going to divide by the V1. So T2 is equal to V2, T1 over V1. So in my calculator, I'm going to be plugging in 0.5 times 361.75 divided by the V1 of 2.3, which is the same thing as I'm going to be doing over here to solve this one. So to solve this one, the first thing I would do is multiply both sides by T2. Now, some people will actually plug in 2.3 divided by 361.75. The reason I never do it this way is I hate maintaining decimal places, right? Because if I plug this in, I've now got T2 times this 0.0063 ... and is equal to 0.5. And then I'm going to go T2 is equal to 0.5 divided by that. So 0.5 divided by the answer, which is going to give me 70, how many sig figs have I got? Oh, only one. So 78.64, which is not my final answer. So let's just leave that for a second. And again, if I plug this guy down here, I've got 0.5 times 361.75 divided by 2.3. which gives me the same answer, right? I'm getting the same answer. It doesn't matter if I rearrange first or what I do. But the key thing here is that this answer is in kelvins. And since my question was in degrees Celsius, I should put this answer in degrees Celsius. So my temperature 2 in degrees Celsius is going to equal that Kelvin temperature minus the 273.15. So we'll go 78.64 ... minus 273.15. Now let's just double check on our sig figs. I said 1, right? Okay, so we're going to go to the tens in my precision. So I'm going to plug in this minus 273.15, and I get negative 194.50 ... which I said that I could do to the tens. So since this answer for temperature was 1 sig fig, this is technically like considered an 80. And so I'm going to go precise to the tens, and I would say this is negative 190 degrees Celsius. The hardest thing about this is the sig figs, to be honest. Okay, let's look at the next question. In this next question, they are giving me V1, T1, and T2, so they're asking me to solve for V2. So again, I'm going to use V1 over T1 is equal to V2 over T2. And if you want to, you could then solve for that V2. Now it's a lot easier for this one because you're just going to multiply both sides by T2. So that you end up with V2 is equal to V1 T2 over T1. I feel like I'm speaking another language. And then I'm going to put in my values. So for V1, I'm going to put in 1.20. And then both of my temperatures have to go in kelvins. So I'm going to convert these both by adding 273.15. So I get 6.3 plus 273.15, which gives me 279.45. And this one, it's all 5 sig figs. And then for this one, negative 5.34 plus 273.15 is going to give me positive 267.81. And again, to 2 decimal places of precision, so I'm going to keep all 4. That's 5, all 5 sig figs. So in here, I'm going to put in for T2, I'm going to put 267.81. And for T1, I'm going to put in 279.45. And then I'm just going to plug this in. So 1.2 times 267.81 divided by 279.45, which, now I've got that volume of 1.20 liters. So I'm going to answer to 3 sig figs and get 1.15 liters as my final answer.